All right. Hello, everybody. Good morning. So I will be talking about something which may or may not be familiar to many of you, a tool set called tracing. And to see why that's relevant for us, I actually was motivated by the early move base. So we just heard a talk from navigation, and the precursor to that was the move base in ROS1. And when 2 years ago I presented at ROSCON a graphic called like this, where we basically looked how long does it take for a sensor message to actually have an effect on the navigation. So if you have a laser scan, how long does it take until it actually affects the driving behavior? And what you maybe can see is, so what's shown here is on the right, on the x-axis is the time as progresses, and on the y-axis is the delay between the laser scan and the corresponding velocity message. And as you can see, this is all over the place. It's not consistent. And so we found out that there was a problem in the ROS move base in the way the various threads were organized that were causing this inconsistent behavior. So where at some points in time we had 20 millisecond latency, and other times we had 200 millisecond latency. And with that, okay, you can, yeah, no. With that, we were able to reduce the latency consistently all through that. Now, you still see a few spikes, but that's just an artifact of the experiment. So what you should be looking at is a low bar there, where you see that we could decrease the latency to 9 milliseconds on average, and we could, most importantly, we could bound it to 20 milliseconds overall. And after I presented that, many people asked me, okay, how did you get this information actually? Because where did the data for this come from? Because you could not, I mean, if you go back to this, you couldn't see this outward from the move base. This is not something that's externally observable, it's all internally to the move base. And the answer to that is tracing. We did it with tracing. And that's what I would like to talk a little bit more today, because now this year we've ported the tracing work that we did for ROS1 to ROS2. It's now actually available in Eloquent by default. And so I would like to show you a little bit about what kind of questions we are addressing with this work, what tracing is then our work on ROS2 tracing, how you can install it, how you can use it, and a little bit of an outlook on what we are planning for the future, and maybe also how you could get involved, because this is certainly not something that's only relevant for us. There's already a bunch of other people in the community interested, and so if you want to join, that would be awesome. Right, so typical questions. This is sort of just a list that came to my mind of the things that I've looked at over the past years. First of them is, this question, how long does my system take to react? That's what we just saw for the move base. We also often have questions of resource use, how much resources is the system consuming. Most people start with, like a big enough box so that everything runs, but then once you want to go to a product, you might want to be a little bit more cost effective, let's put it that way. And then also, if I have an information about what the typical resource use of my system is, then at runtime I might want to monitor whether my system is still in the expected corridor, or whether there's maybe something happening that shouldn't be happening. So all of these are not new questions, but there are a couple of complicating factors in ROS2-based systems, and the first of them, it's a distributed system where we have many processes running concurrently, sometimes even on different machines. And also we have repetitive periodic processing, but so the assumption by many people is that if it runs for one cycle, it always runs correctly, but this is simply not true. And of course, if you want to do this at runtime, it should better be low overhead. And this is true for both general performance analysis, where we don't want to affect the system that is measured, but it's for execution monitoring. If you want to run it continuously, of course, it's even more important. So tracing, what's tracing? Basically, tracing is defined as recording information about the system's execution. The way this basically works is that you first have to instrument your system. You're putting specific trace points, what they're called trace points, into your system. And this is so that you can, this is basically for overhead reasons. You know, if you know about profiling can basically, you know, you can profile your whole system, but this will typically cause severe overhead. And with tracing, you can put trace points exactly at specific locations that you know are important, and then the overhead is much less. Then at runtime, what you do is you configure it, because so people basically put a lot of trace points in there for everything you could conceivably be interested in, but then at runtime they only enable a few of those, again, typically for overhead reasons, and you all have to store all this data. And that's what, when you run the system, you store trace data, and then typically in an offline stage, you analyze the data. This can also be done live, but I'm showing here it's done offline, and so that's what many people use. Just to give you an idea of what kind of information can we record, this is a picture by Gregg, one of the, if you've ever looked at tracing, you will know his name. He's at Netflix, he's a system architect there. He's worked a lot on tracing, he popularized it a lot. He made this image here, and that's basically the kind of tracing information you have in a Linux kernel. And you see that almost every subsystem has a couple of trace points in there. And you also have trace points for hardware features that are basically CPU counters. And there's also a split between user space and kernel space. In kernel space, you have kernel probes, and user space, you have user probes. And you can, it's in basic, but you can still look at, and one of the big advantages of tracing is that you can look at all of these information together if you want to. And that's, for example, one of the things we often do. We look at the scheduling behavior of the kernel together with the callback behavior in the user space, the ROS2 nodes. I will show that later. Just to give you an idea of what kind of information, this is basically also one of those famous images, is called flame graphs. So what's done here is that you look at how much, what the duration of the various functions in your program is, and obviously some functions call other functions, so this is a recursive process to some extent. And so this basically here at the lower level, it's the whole process, and then you have, for example, a page fault function, and this does do page fault, and then in there is a handle memory fault, and so on. So this, and you get the idea of where most of the CPU time is spent fairly quickly with these images. So having said that, let's look at ROS2. I hope this image is hopefully clear. So we look at the various layers in the ROS stack, and they have various components, and I put here some the places where we currently have trace points. So we have two kinds of trace points. One of them is for initialization. So whenever you initialize a ROS2 thing, then you will get some information about it from tracing. And then there's the other kind of trace point, which is an invocation trace point. And this is typically what occurs when your system is running. So whenever you get a message and a callback is being called to process that message, then you get an invocation trace point. And so you see that on the RCL layer, on the RCL CPP layer, we are fairly complete. RMW is at the moment not instrumented because it's not very interesting to us. Most of it is just passed through to RCL anyway. One thing that would be very interesting is instrumenting the DDS layer. The difficulty there is that obviously, as you know, there's multiple DDS implementations, and some of them are not even open source, so it's a bit more difficult for us to go in there. And also, if we could instrument some of that at the RMW layer, but even then we would have to do it for all the implementations. So that's why we currently haven't done it. If any DDS vendor out there wants to collaborate here, that would be awesome. Just saying. So, what is it? How does it look like? So the first thing is what we're doing is mostly called static tracing. And static tracing is where you have the trace point defined at compile time, inserted by the developer of the code or by a system engineer. And the advantage of that is it encodes the knowledge about what is important, and has direct, because it's in the source code, it has direct access to all the data that you have in using the normal programming language features that you have. The disadvantage, of course, it takes effort, right? You have to put it in there. And also the way you put it in there can be dependent on the tracing framework that you use. There is some general stuff, but for example, we are using, so there's various tracing frameworks on Linux. There's, for example, Linux Tracing Toolkit. On Windows, there's the event tracing framework and so on. So this is different. So what we did is basically, on the one side, you see Linux Tracing Toolkit definition of a trace point. So this is basically a callback start trace point here. I hope you can, I don't know if you can see that. Let me just check. Late pointer. Can you see? Yeah, I should see. So here, this is callback start. This is what it's being called. These are the argument definitions, you know, like what you get in, and then you have to store the information on how this is stored. But in the code, it's basically just called like trace point. That's a macro, and then you give it the name, and then you give it the arguments. And so this is, for example, in the dispatch function of the executor for ROS2. So what we're trying to do here is we're defining an abstract macro interface for you so that in the ROS2 code you can just use this macro, and then on your platform it's mapped to whatever your platform supports. At the moment we only support Linux, but in this approach we could also add support for Windows as well, or for macOS tracing. I know Windows has tracing. I don't know if macOS actually has tracing, but I would assume so. It's a fairly common technique. Where I would also like to mention that there is a way to have runtime tracing. So this is, well, there's various methods of doing that. They're a little bit more complex. But the advantage is that it's you don't have to be able to modify the program that you're tracing. And I'm just mentioning this. We didn't do this, but it's something that you might want to do for your code to get some more insight into your own code without having to modify it. Just so you know that's out there. If you want to use this, talk to me, can give you more info. Right, so how do you use it? We have a tutorial here, it's linked up there. There is some prerequisites. As I said, we are using Linux Trace Toolkit. By the way, the reason we're using this is because it's the least overhead version of tracing available. And there is also a library called Babel Trace, which is for reading the trace data. So basically, for all of that, you have to add an apt repository. Well, because even Ubuntu 18 doesn't include the most recent version that you need for analysis. And it's a bunch of modules you can get. Then we have modified repos, you can just build them. And so that's what you still have to do, right? So the trace points themselves are in Eloquent, but they are not turned on. That's because the OSRF is concerned about performance. I mean, we could talk about that, but it's just the way it is right now. So what you have to do is you have to get the trace tools into your workspace. It's a fairly small library. It doesn't take long to compile. And then once you've done that, you can trace everything that's out there. You don't have to recompile the ROS2 system. You just have to recompile the tracing library. And that's how you do that. And there's this with LTTNG on, that's what you have to pass, and then you go. And then what you want to do, there's two options if you want to execute your application actually with tracing. There's two options. One is ROS Trace. ROS Trace basically works exactly like ROS Launch, but it traces your application. And then there's the trace action. The trace action is a bit more explicit. It's something that's can you put in your launch file. It allows you to configure the tracing a little bit more. Here's an example. So for example, here you're giving your tracing session a name so that you can distinguish this. And this could also be used to only trace part of your system. You just put the trace action into the part of your system that you're interested in. And that's just it. You just add this trace action and then you launch it and then you're good. Then it's being recorded. And once you terminate the launch, the recording ends and then you can start analyzing it. And to give you an idea of how this analysis looks, we have a couple of default analyses. One of them is kind of useful for figuring out how long your computations take. So it's just to ROS2 run, trace tools analysis, and then you have to know a bunch of scripts. One of them is callback duration to give it the pointer to where you stored your data. You can have multiple sessions, of course. And then it gives you an information like this, where you say, okay, I have a function here. It's in Pong node. It's a lambda, so I don't know the name of the function, but it takes a string parameter. This is being called 17 times for a total of 1.7 milliseconds with a mean duration of 0.1 millisecond and some standard deviation for that. And this is what you do. So you see here that we have these two lambdas. There's the, I don't know, the ping node. I don't know actually what that does. And then we have two parameters, which are, there's a bunch of parameters being configured, but all of these calls take a very short time. And of course, you can also graphically visualize that. So this is just the same kind of data visualized using Jupyter Notebook. So we have an example Jupyter Notebook in the source distribution. You can just open it, and it tells you, you know, how to load the data, and to give you a plot like this. Just again, the callback duration over time. What we see here is very typical. Usually, the first calls take a bit longer when the system is still starting up, and then we have more or less a steady state of how long it just takes during execution. Right. So that's what's there by default. You could do more analysis with this. You could analyze the data that you get by default for more than just runtime duration. You could also look at the ordering. You could look at counts. You could look at memory consumption and so on. But typically, what I find is that when I really, this only gives me a very broad overview. So I can run this on my whole system. That's one of the advantages. I get the visibility on all nodes that are there, so I can typically quite easily see where there might be a problem. But then when I want to look at the problem, I need more information. And there's, fortunately, a way to have custom trace points, which are integrated with the other tracing. And the way we did this is, you probably know that GCC has this f-instrument functions argument, where basically then for every function call, they insert profiling call. This has way too much overhead by default, but what we did is so like Christoph, who is the intern who was working on this in the summer a lot, he created a very cool GCC plugin where you can basically put an attribute in your code, and then it will instrument those functions, just those functions, nothing else. And then these kind of things will be included in the tracing. And this is what we did in the summer. We looked at the executor, and we did exactly this method. So we instrumented a bunch of functions, collect entities, add handles to weight set, RCL weight, and remove null handles. And that's again one of the analyses that we did this summer that you might have heard about. And this has been done using the custom trace point implementation. And to give you a little bit more background on that, as dashing was released, several people noticed that the ROS2 executor is actually not very efficient. I should say this depends very much on your workload. If you have a lot of very small functions, and if you have a lot of messages coming in, then the single-threaded executor adds a significant overhead. We knew this, but we didn't really know where it came from. So that's, again, perfect for tracing. And here, this is one of those things where we included both kernel information and user space information into the trace. Because what you can see is that from the user, so we also always had on CPU only. So before, what I showed was just duration. So like if you call your function and it takes 5 milliseconds, you get 5 milliseconds. But maybe if you call the function and it in there is asleep for 3 milliseconds. So that's of course different than if the function would be computing and occupying the CPU for the whole time. And that's the kind of information you get from the scheduler. So you know when the program is actually on the CPU from the Linux kernel scheduler, and that's being included here. And so this information only includes the time that the function actually spent on the CPU. And that's quite relevant because here internally there's RCL wait. RCL wait is the function that waits for new data from the middleware. And obviously if there is no new data, this will wait. But what we are interested in is just the CPU consumption of the function. That's why we wanted to exclude the wait time. And so what you can see here as a result of that is that the actual middleware functionality is in green, and the other blocks are what ROS2 adds as overhead. And so you can see that is quite significant. It's about 70% of the total processing time in this benchmark. That always needs to be set, right? This is a very specific benchmark, which is is specifically created to bring out this problem. This might not affect your system so much. I always, like when I presented this at ROSCON, lots of people were coming to me and saying, yeah, well, we can't use ROS2, it has so much overhead. I really have to say this is only in the benchmark. But anyway, what we found this out, it was quite interesting, so now we could look at it. A company from the Netherlands called Nobleya looked at this and improved it, and now it's much faster if you have their static executor, and this is going to be in ROS2 in the future. So just to give you an idea of how this affects the development. Right. Having said that, what are we going to do? We want to improve the trace points for services. We already have them in a service server. We don't have them in the client yet. That was an oversight. We want to provide more analysis so that you get more useful things than just durations. Analysis also takes quite a bit of computation right now. We want to improve that. And we would like to have live tracing so that you don't have to run your system and only have post-hoc analysis, but you can do this online. And eBPF tracing is something that's in the kernel that's very cool and flexible. We also would like to integrate that. Let me just shortly conclude here to say that I think tracing is an excellent infrastructure for this kind of system-level analysis. You can inspect the whole system and integrate kernel user space information. We have contributed an initial tracing instrumentation for ROS2 with trace points in the framework, with integration with tooling, and with basic analysis scripts. And I think this is really just the start. We could go a lot further with this if people are interested. And just to maybe say a little bit, our goal, for example, you saw with Matt's talk before, he said, you know, like they're at 95% pass rate. Of course, we would like that to be 100, and maybe tracing can make a contribution to that sort of analysis also. And that's all I have to say for now. Thank you for your attention. Okay.
Yes, thank you, Ingo, for this interesting talk. Do you have any questions? Yes.
I can just speak.
Okay.
So just wondering, you said that tracing right now is disabled in ROS2 because OSRF has some concerns. What's your opinion about the performance impact? Because you seem somehow a bit skeptical.
I mean, so tracing has all the tracing frameworks have been specifically designed to not have significant, not be noticeable when they are disabled. So this disabling functionality is already in the tracing framework. But so what's basically happening is you have one call to a different shared library, and this call immediately returns. So if you put this call into the innermost loop of your computational process, then it might affect your performance. But what we are doing is we are putting this call before the typical average call, also like once per callback. And there's so much else going on that just one call that immediately returns. I wouldn't see this as a performance issue, because if it's disabled, it doesn't do anything. So that's my perspective, that tracing frameworks have been already designed to avoid overhead. But they were concerned about this because it's in every, it's on every call chain, right? So, and there's multiple trace points, and so that's why we made this decision to have it really be able to compile out entirely, and that's just the situation there. I think that when we get more experience with this and we notice that the overhead really is negligible and maybe have more data also, on tiny systems, not just on big, powerful systems, then eventually we will be able to have this in there all the time.
Thank you.
Yeah.
Thank you, Ingo. So we might have time for one short question if there's another question here. If not, thank you, Ingo, for the presentation. And,